So let's first analyze the behavior of the conservation law equation on the smooth region. So if you think of back over here, over this previous solution, we want to analyze the behavior of this equation on somewhere other than this discontinuity, like over this region, for example. How does it behave? And if you take a look at the contour in space and time, let's magnify a little bit. Can somebody describe to me how the solution behaves? Is there something special you see on the space-time plot? Yeah, there is a discontinuity. Let's talk about this later. Right now we are talking about smooth part of the solution. That's right. Do you see something special on the smooth part of the solution? What do you see? A lot of what? Dispersion. Huh? Dispersion. I'm just don't interpret it yet.
Leaning inwards.
Huh?
It's leaning inwards.
It's leaning inwards. Yeah. What else? What do you see on this plot other than colors? A bunch of lines, right? A bunch of not just the regular lines, a bunch of straight lines. Does it occur to you as non-obvious that the contour of a function should be straight lines? If you draw an arbitrary function of space and time, you would expect I get curved contours. It's not common to see functions in 2 dimensions with straight lines being contours, right? So why do we get straight lines? I mean, that's actually not the case when you hit discontinuity. For example, over here, we don't get a straight line. We get a line that actually turns, right? 2 things hit into each other and it turns. So, but on the smooth portion, you see all straight lines. So why do we see straight lines, and what are these lines? That's a great point. So you already did the analysis I wanted to do. So that analysis is from the differential form of the equation, right? So if you go back to the differential form of the equation, partial u partial t plus df du times partial u partial x equal to 0. Okay, and we said this is the wave speed. And if f is only a function of u, then df du is only a function of u. That means the speed at which the wave propagates, they are just a function of u. So as the wave propagates at, for example, towards the right, because if I'm riding along the wave, then locally the solution value u doesn't change, and therefore the speed doesn't change. Intuitively, that's the answer, right? Mathematically, let's do a little bit of analysis. So if we look at the differential equation, what we can do is we can write the solution u at a particular x plus or minus x plus df. So let's just do this, x plus a ct. So let's look at a function along the value of the solution along a straight line on an xt plot. So c is going to be the slope, so it's going to be the slope of dx dt. So basically this is 1 and this is c, right? I mean, it's not the slope, it's kind of the inverse of the slope. Okay. So the derivative, so now because I wrote u as a function of not x plus ct, so x plus ct is x and also t. So this is x, this is t. Does it make sense what I'm doing? I'm looking at a function of the solution along a line. So basically, if I make x a dependent variable of t, then I reduced u into a single variate, univariate function instead of bivariate function. X plus, I think. So basically, this, let me use x naught to be to be distinguishing from this x. So this is x naught, this is t equal to 0, right? So as t increases, x is going to increase by c times t. All right. Okay, so this function, if we fix x naught, is just a function of t. So let's look at what is du of x naught plus ct t dt. Again, we are using chain rule. So this is equal to partial u partial t times d x naught plus ct dt plus partial u. Oh, sorry, this is partial x, right? I am differentiating towards the first variable, partial u partial t times 1. So this is dt dt. And what is this? What is the first term? It's just c, right? So this whole thing is equal to c times partial u partial x plus partial u partial t. Now let's go back to the original differential equation. According to the original differential equation, this whole term is equal to 0 when c is equal to what? If c is equal to df du, this whole thing is going to be equal to 0. So there is a chain reaction here. So if I choose c to be equal to df du at x equal to x0, 0, and t equal to 0, okay, then I know that the time derivative of u along that line is going to be 0, which means along that line my u is going to be constant. My u is going to be constant tells me that c is going to be constant. So that means I can go along straight into that line and expect my solution to hold constant, not changing at all. All right, does it make sense? And that is why we see a lot of straight lines on this contour. A contour is a line on which the value of a solution holds constant. And these contours are characterized by these lines, x equal to x naught plus c. So this line is you can either write x equal to x naught plus ct, or you can write as x minus ct equal to constant. I mean, either way is fine. I think maybe you are thinking about this, right? So if x minus ct is a constant, that also represents that straight line. All right, okay, so now another question is, how does the slope of the line depend on the local solution? The slope of the line is the inverse of df du, right? So if I have a df du locally equal to 0, for example, what kind of line should I get? I get a vertical line, exactly. If df du is equal to 0, c is equal to 0. I get a vertical line. What if df du is negative? I get a line that is tilted towards your left, right? If df du is positive, I get a line that tilts towards your right. And again, let's look at the Burger's equation to see how does my df du depends on u. So Burger's equation, if f of u is equal to u squared over 2, df du is equal to u, then u less than 0, I get negatively sloping contours. U equal to 0, I get vertical contours. U greater than 0, I get rightward tilting contours. Let's look at this to see if that's the case, right? So when u is positive, the color is u, I get right sloping contours. When u is negative, I get left sloping contours. And when u is almost 0, towards here and here, I get vertical contours. And the more negative I get, the more leftward sloping I get. The more positive I get, the more right sloping I get. So that's the contours we call characteristic lines. So these are the characteristics lines of my solution. X equal to any x naught times df du locally, df du plus t. Not this way, the other way, I think. X plus df du times t are called characteristics. All right. So when we solve nonlinear conservation laws using any numerical methods, we should expect to see these characteristics.